Hi and Assalamualaikum warahmatullahi wabarakatuh. Today, our group, which is Group 3 from class KCCS 1102E, we will doing MAT 183 video presentation in solving a question on a topic, application of differentiation, applied maximum and minimum problems. What is related rates? Related rates are rates of change associated with two or more related quantities that are changing over time. So, why do we use related rates? Related rates helps us determine how fast or how slow a certain quantity is changing using the rate of change of the second quantity.
Now, for our problem statement, a rancher has 200 meters of fencing with which to enclose two adjacent rectangular corrals. A. What dimensions should be used so that the enclosed area will be at a maximum? B. Find the maximum area enclosed.
Okay, first things first, let's take a look at our given image. We have two adjacent rectangular corals, which means we have 5 sides. You must wonder, why 5? This is because we have two enclosed spaces, which means we have to include the middle part of the image. By adding all 5 sides of the image, we can get the perimeter, which is 4x plus 3y. Moving on to question A, what dimensions should be used so that the enclosed area will be at maximum? This means we have to find the maximum value of x and y. First things first, we need to express y in terms of x. With the perimeter equation that we had in the previous slide, we are also given the information that the range is 200 meters. So, we can equal our equation with 200 meters, so 4x plus 3y equals to 200, and move everything that is not y to the other side. And we will get y equal to 200 minus 4x divided by 3. As for the equation for the whole area, we will have to times the length and width, which is a equal to 2x times y. After that, we can substitute the y equation that we got into our area equation, so it will be a equal to 2x times 200 minus 4x divided by 3.
So, to find dimensions, which is the max value of x and y, first step is find the first derivative dA per dx using product rule. dA per dx equals to uv prime plus vu prime. U equals to 2x and u prime equals to 2. Then v equals to 200 minus 4x per 3 and v prime equals to 4 per 3x. dA per dx equals to uv prime plus vu prime. dA per dx equals to 2x times 4 per 3x plus 200 minus 4x per 3 times 2. Then dA per dx equals to negative 16x plus 400 per 3. To find x, we need to do step 2, which is let dA over dx equal to 0. From the previous slide, we got dA over dx equal to negative 16x plus 400 in a bracket over by 3. So, for the step 2, we need to substitute dA over dx equal to negative 16x plus 400 in a bracket over by 3 equal to 0. Then, 16x plus 400 equal to 0 times 3. That makes negative 16x equal to 0 minus 400. Next, x equal to negative 400 over negative 16, and the final answer for x is 25. To check if x is the maximum value, we need to do step 3, which is the second derivative test. D, the power of 2a over dx the power of 2 equal to negative 16 over 3. Negative 16 over 3 is less than 0. Hence, x is equal to 25 is the maximum value. For the last step, Step 4 is to find y. Substituting x value in previous equation, which is y equal to 200 minus 4x in a bracket over 3. Y equal to 200 minus 4 times by 25, which is the value of x in a bracket over by 3. For the final answer for y is y equal to 100 over by 3. So, at the end, we got the answer for x is 25 and the value for y is 100 over by 3.
Now, let's look at problem solution for B. Find the maximum area in groups. To find the maximum area, we have to substitute x and y maximum value into area equation of rectangle, length times width. Now, the maximum value for x is 25 and the maximum value for y is 100 over 3. Then, we substitute the value into the area equation, 2x times y. That will be equal to 2 times 25 times 100 over 3, and we will get the answer of 1666.67 meters squared.
In the topic of the application of differentiation, specifically in applied maximum and minimum problems, the goal is to find the highest or lowest value of a function within a given context. By using differentiation, we can analyze the behavior of the function and identify critical points where the function's derivative is 0 or undefined. These critical points can correspond to maximum or minimum values of the function. Through further analysis, such as the use of the first and second derivative test, we can determine whether these critical points indeed represent maximum or minimum points. This approach allows us to optimize various real-world scenarios, such as finding the maximum area or minimum cost in engineering, economics, physics, and other fields.